Hello, everybody. Every time I say that, I think of Dr. Nick from The Simpsons. I don't know if anyone watches The Simpsons anymore, but anyway, folks, you gotta be on your game here today. There is lots of information coming your way in this particular lesson. Okay, for sure. You might have to stop and pause and play again at some point. So, a couple of definitions. First of all, a secant is a line that intersects a circle in two places. So, for example, that red line would be called a secant. All secants would contain a chord. So, obviously, you have chord AB, but a secant is a line. Okay? Now, we've used the word tangent before in trig. Here we're using tangent a little bit differently. Tangent is a line that intersects a circle at exactly one point only. Now remember, a line goes forever, so you can't just draw a line and just stop it there and say that's a tangent. That's not right. A tangent just comes by and nicks the circle. Okay, and let's say that's the center of the circle. So that's the excuse me, the blue line is the tangent line. Now there's just some information here. It says a tangent line is perpendicular to the radius drawn to the point of contact. So wherever you have a tangent drawn to a circle, if you draw a radius to that point of contact, you are creating a right angle. Okay? Some other information. If a line is perpendicular to a radius at its outer endpoint, then it is a tangent line. That's essentially the converse, right? If this is big. If two tangent segments are drawn to a circle from an external point, the segments are congruent. Let me show you what I'm talking about. So if I had a circle and I selected some point out here and I drew a tangent down there and a tangent like that, what we're saying is AB is congruent to AC. Okay. All right. So there's three big types of problems that we're going to talk about today. I know it says two, but the second type has a subset of two, so there's actually three altogether. The first is called a walk around, and these are kind of neat, and I'm going to kind of take you through this one. By the way, you're not always going to be mentioned that things are tangent, and I apologize for that. Here it does say circle P is tangent each side. Sometimes you're going to be assuming the tangent C. What we're going to do here, this problem guides us. It says let AQ equal X. Now, this is a tangent segment, and so is that. And what we just talked about above, that means that this segment is congruent to that segment, so this segment must also be X. Now, I'm going to mark in the given information, but I'm going to do it a little bit out of the way. It says AB is 20, BC is 11, this is 14, and you'll see why here in a moment, because I need some room to work. Now, if this is X and that's X, and this whole thing's 20, this little piece here, remember X is from here to the tangent point. This piece here would have to be 20 minus X. And now you see that's a tangent segment, and so is this. So this would be 20 minus x as well. You see what we're doing now? We are now walking around this figure. Now, if this piece is 20 minus x and this whole thing's 11, this would have to be 11 minus that. Now remember, folks, don't make that mistake. 11 minus this quantity. You need parentheses. So this 11 minus 20 becomes negative 9, but minus a minus becomes plus x. That's that little piece. This little piece is the same thing. Now this, of course, would be 14 minus that. 14 minus that, you'd get 23 minus x. You'd get 20, and you see we have walked around the whole thing. Look what happens with this segment. That's what we're asked to find. AD, the x is what? The x's cancel. Now that's one type of walk around problem. We started in one spot and we walked around in one direction. Sometimes you'll start in one spot and walk around in either direction and meet on the opposite side. I'll show you one of those in a moment. But I would like you to see if you can try this one yourself. So, this circle's inscribed in this triangle, inside this right triangle. It's kind of neat. It ends up being super easy, but only if you see the right relationship. WY, let's mark this given stuff. That's 20. We know that this radius is 4. You're going to want to draw a radius in some place. I would like you to pause this and see if you can kind of give this a go yourself, and then I'll walk through it in a moment, okay? All right. Now, hopefully you tried. Drawing a radius here does us nothing. We want to draw a radius in to the point of tangency. That creates right angles. We're actually created what here? We created a square, right? Okay. If that's 4, we were given that's got to be 4, so is that. Okay. Now, you just have to call something x. I'm going to call this x. That means this is x. That means this is 20 minus x. Oh, wait a second, that means this is 20 minus x. And then sometimes people wonder, well, what do I do now? Well, you're done. Check this out. If you find the perimeter, if you add these up, 20 minus x plus x plus x plus 4 plus 20 minus x plus 4. What happens to all the x's, folks? The x's all cancel. And we actually get a perimeter of 48. There you go. All right. This next one, again, try this yourself first. This is one where you are going to want to, I'll kind of help you get started. Well, actually, it doesn't really matter here. You're asked to find the radii of all 3 circles. So just call one of the radii, I'm going to call this x. Okay, and see if you can't, I got disappearing ink, that's annoying. See if you can't do this on your own and come back here in a moment to check on my solution, okay? All right. So I've got this distance to be 8, this distance to be 13, this to be 11. I'm going to walk around both ways here. Makes it a little bit easier. There's less of that annoying subtraction. Watch. There's a radius. That's a radius too. This has to be 8 minus x. This has to be 8 minus x. And I'm gonna instead of walking around in the same direction, I'm gonna go back over here. This is 13. So that's 13 minus x, and so is this. So these two things here, the sum of those things has to be 11, right? So we got negative 2x. What is that? Plus 21 equals 11. Negative 2x equals, sorry, my computer's wigging out there. I don't know why I wrote down this negative 11. Let me fix that. Negative 2x equals negative 10. So x equals 5. So obviously that's circle B. B, the radius of B is 5. A would have to be 3 and C would have to be 8. So there are your walk around problems. So I ended up doing 3 of those. I hope you tried some of them yourself. See some in your homework, of course. Now go back and look at this again if you need to. All right, now we have 2 more types of problems. We have a common tangent problem, but there's 2 subtypes. There's a external tangent and an internal tangent. So the first thing here, it says the centers of 2 circles of radii are 10 and, the centers of 2 circles of radii 10 and 5 are 13 centimeters apart. The centers are 13 centimeters apart. So if the radii are 10 and 5, how are we going to draw these circles? Do we draw these circles with a gap in between them? Do we draw them just touching each other, or do we draw them overlapping? And I hope you realize quickly, if the radii are 10 and 5 and the centers are 13 centimeters apart, we have to draw them overlapping. And that's what I'm going to do here. Okay, so there's my circles, and you always want to connect the centers. Always connect the centers. Now you really got to be paying attention here. So here what we're going to do, the question's actually missing here. I don't know what happened there. The question should say find the common external tangent. Okay, so the first thing we have to do is draw it. Common external tangent means a tangent that is, get rid of this, tangent to both circles. So there you go. Okay. Now what we do, once we draw in that common tangent line, we want to draw radii from each of the circle center. Now remember, a radius to the point of tangency creates a right angle. So if you've drawn this correctly, these 2 radii that you've drawn should look parallel because these 2 segments are both perpendicular to the same line. They are parallel, all right? They are parallel. Now remember, we know that this distance is 5 because we're told that small circle's 5, big circle's 10. Now I'm not going to label that yet. This next part's the magical part, okay? So we drew our 2 circles, we drew in the common external tangent. You're always going to draw in these radii to the point of tangency. Now in a common external tangent problem, the next step is key. You are going to take your pen and pencil and put it on the center of the small circle. Repeat after me, center of the small circle. You are going to drop in an altitude across this figure, therefore creating a rectangle and a right triangle. Now, this is not drawn to scale by any means, because look what happens now. If this is 5 and we created a rectangle, this is 5 as well. because you're given that this whole radius is 10, that must be 5. Now, down here, remember, we were told that the centers were 13 centimeters apart. We just created a right triangle right in here, and that dash segment is going to be 12. We have a triple. Remember, the 13's in the hypotenuse position. That's a 5, 12, 13. Now, if the dash segment is 12, AB, that's what we're finding. That's got to be 12 as well because you're dealing with a rectangle. So the common external tangent is that segment that connects the two tangent points. All right. Just got a couple more to do here. Here's another one. This is also external tangent. So if you want to try this next one yourself, you certainly may, number 2. Okay. And then I'll talk through it here in a moment. It's the same type of thing. You're just going to think about what it means for circles to be externally tangent. If you're not sure, you can watch what I'm going to do here and then try the problem. Externally tangent means the circles just nick each other. All right, you guys pretty impressed with those circles? And we always connect the center, and then I'm going to go ahead and draw in. I could draw in the external tangent up here. I could draw it in down here. It doesn't matter. Just do the best you can. And again, remember, you're going to draw in radii to that point of tangency, and those radii should look parallel. Okay. Circle with a radius of 8. Boom. This one's 18. We'll deal with that later. Now remember, that means that this whole segment, because they're externally tangent to each other, this is 8 plus 18. So this whole thing is 26. You may have thought that we didn't have that information, but we do. Now again, pencil on the center of the small circle. Draw in that altitude. We created a rectangle and a right triangle. If this is 8, that's 8. If this whole thing's 18, this must be 10. We just created another triple. This is a 5, 12, 13 triangle doubled, so you're going to end up getting AB is 24. It's not always going to be a triple, folks. Okay, last one, and this is new. This says internal tangent. Now, if you look at this, we have radii 3 and 5, and the centers are 10 units apart. So we're actually going to draw circles that are have a gap in between. Connect the centers. You always connect the centers. Okay, now this is not an external tangent. An external tangent would be out here or down there, okay? The internal tangent crosses the line connecting the centers. So in other words, there's 2 of them. I'm going to draw right here. We don't need to draw them both. I'm just going to draw one of them. Obviously, the other one would be right there. Okay? So it's still tangent to both circles, and it's just that this one crosses the line connecting the centers. Now, just like we did before, we're going to draw in radii to the point of tangency. And again, those radii should look parallel because they're perpendicular to the same segment. Okay, we're almost there. Radii of 3 and 5. This one's maybe a little bit trickier. Watch what I'm going to do here now. I'm still going to create a right triangle and a rectangle, but I'm going to do a little bit differently. There's 2 different. I could do this in 2 spots. I could I'm going to extend one of these radii. I can extend this one, or I can extend this one. It doesn't matter which one I'm going to do. I'm going to do this one down here. But watch, what I'm going to do, you see this length of 3? I'm going to extend this radius of 5. I'm going to extend it the same length as this. And I'm going to connect these points here then. And now I have created a rectangle here. All right, I've created a rectangle. Remember, what I want to find here is the length of AB. Now, I've also created, my computer will come back in a moment. I've also created this big right triangle here. Okay, now look, we got a leg of 8. And remember, the distance here between the centers is 10. So I have a right triangle with a hypotenuse of 10, a leg of 8. That means this has to be 6, 3, 4, 5 triangle. Now, if that's 6, AB must be 6 as well. So that's the internal tangent problem. Pause that, stop it, rewind it, take a look at it again. It's the same procedure every time. You're always connecting the centers. You're always drawing radii to the points of tangency, and you're creating a right triangle and a rectangle. A little bit different though with the internal versus external, but please rewatch those as needed. All right, I'll see you.